You're doing 70 miles per hour down an empty stretch of highway. The trees blur past your windows. Suddenly, the yellow truck in front of you locks its brakes. Surviving the next 5 seconds relies on a single question. How do you calculate the specific distance required to stop? Predicting that outcome and keeping your front bumper intact requires understanding the specific variables that define motion. Before we can measure movement, we have to pin down a fixed starting point. In physics, we call this the reference point, or the origin. Take an athlete sprinting down a track. If we mark her starting block as position 0, every step she takes is a measurable change relative to that origin. She sprints to the 100-meter mark, turns around, and returns to 40. Her total path is 160 meters. That's distance. But her net change from the start is just 40 meters. This direct measurement is displacement. Distance and displacement only match if the object moves in a single direction. The moment she turned back, those two numbers drifted apart. Displacement isolates where an object actually ended up. By ignoring the winding path of the journey, it provides the precise coordinate needed for further calculation. Once we have that coordinate, we introduce time to calculate speed, the rate at which that distance is covered. However, knowing how fast something is moving doesn't help us track its path if we don't know where it's headed. When speed is combined with a specific direction of travel, we get velocity. Because velocity is direction dependent, steering slightly to the left changes the data, even if the speedometer stays perfectly steady at 70. Tracking velocity allows us to project exactly where an object will be at any future second. In the real world, motion is rarely a smooth, unchanging cruise. Objects speed up and slow down. The rate at which that velocity changes over a time interval is called acceleration. Think of a massive diesel train starting from a stop. It takes immense force and several minutes to build up its velocity, showcasing positive acceleration in action. But consider this. Can an object have zero velocity and still be actively accelerating? Look at a basketball thrown straight up. At the exact peak of its climb, its vertical velocity hits 0. Yet throughout that entire pause, gravity is accelerating it downward at a constant rate. Factoring in this continuous change is how we bridge the gap between steady, idealized motion and the complex physics of the world around us. When an object moves with a constant acceleration, like a steady brake pedal, we can use specific formulas known as the kinematic equations. These equations rely on 5 variables: displacement, time, initial velocity, final velocity, and acceleration. They allow us to relate these values to one another to find a missing piece of the puzzle. Returning to that truck on the highway, by taking your initial velocity, the vehicle's braking acceleration, and a target final velocity of 0, you can determine the exact stopping distance required. These equations provide the mathematical framework to calculate the physical limits of a vehicle's motion before a collision occurs. We can even apply these rules when we move from straight paths into continuous loops. In uniform circular motion, an object maintains a constant speed, yet it is also constantly accelerating. This occurs because the direction is constantly shifting. Since velocity includes direction, any turn is a change in velocity, meaning acceleration happens at every degree. From braking on a highway to the mechanics of an orbit, these rules provide the coordinates and rates needed to navigate a world in constant motion.